let's get started to our sixth lecture on Introduction to AI. And today we will talk about constraint satisfaction problems. Yes, there's no sound, there's no picture. All right, well, there's sound from me, but there's no picture on the big screen. Right there. So, of course, as usual, the material is actually from the sixth chapter from the global, I think. No, global edition has fifth chapter. This is actually sixth chapter in the American edition, actually. Two different versions of the book. They say, okay, this comes before adversarial search, game search, or after. It's actually kind of its own, I would call this a side quest. It's actually a separate tool. And so what are we talking about here? We are talking about a situation when we have a general problem. We are looking through our states, meaning different variables representing our states, and we have some sort of limitations. So it's a general sort of limitation, and it could be used, quite a bit actually to solve these type of problems, basically. Again, why do we use these type, why do we model problems as these? Because they are there exist efficient tools for solving these type of problems. Again, it's not the only tool. Again, there might be different ways of solving some problem, but if you see, okay, this is a constraint satisfaction problem, you have already pre-made solutions in mind. Again, so if your agent encounters this type of problem, you have sort of, okay, we'll use specific algorithms for solving it. Okay, so let's define it. This is from the book, and maybe I'll again use my friend Paint, right? So again, let's do a formalism, right? So basically, which will solve this problem, basically, right? So the book says XDC, right? So XDC, right? X would be a set of variables. Let's say x1, x1, x2, and so on, right? That's what we can change, right? And we have domains, right? On constraints. I believe we call them C, right? Something like this. And basically, these are tuples that will meet the solutions, right? So I'll give you a concrete example, right? If we have, let me see how we write formally, but basically, I think it's called x1, x2, right? On x1 has to be more than x2, right? It's really silly, a really simple constraint. I think they might use it like this. Okay. Now, of course, the question is, what is the x1 and x2 values, right? You have to say what's the domain of them, right? So if it's all natural values, you have infinite solutions, really, right? But if we say that these x1 and x2 are, let's say, numbers from 1 to 3, right? Then we are left with how many solutions? Let's assume. Let me see how would I write this formally. I don't really. How would I write this formally? That x1, x2, right? Oh yeah. So x1, x2, both values, right? Actually, domain will be 1, 2, 3, right? Let's do this. 1, 2, 3, right? That's a allowable domain. Let me erase this. Actually, I guess. Right. X1, 2, 3, right? So this is what we can use. 1, 2, 3, right? And that's basically this the demand. So if I can write only 1, 2, 3, right? Then what's the solution? Again, it seems silly, right? Come on, where's my fat brush? Let's use a fat brush. All right, there we go. Okay, now, so for x1, x2. x1, x2, I guess, right? Okay, so I want some solutions, right? So x1, x2, I want tuples here, right? So how many tuples I have? I can think of at least 3 solutions, which will be x1, x2, or x2. That's the domain. You can go outside. So this is like, come on, first grade.
32, 31.
Yeah, so 3, 2. That's legal, right? Meets constraint. So 3, 1. And what's the other one?
2, 1.
2, 1. All right. And that's it. And we solved this particular problem, right? We don't need any special tools, any algorithms, right? We can give it to our kindergarten, people, right? So, or little sisters or brothers or, I don't know, children. So, yeah. but it works, right? So that's the formal way of specifying. Of course, things get very complicated when you add more and more variables, right? Variables, right? X3, X4, and so on, and you have constraints grow, and of course your domain basically can, solutions could become numerous, or maybe they're none, right? So again, but this is the formal way of defining this, basically, right? Again, so we'll see different ways of solving it, but that's general idea, right? So set of tuples, right? Assignments, right? So we need to respect the rules of the game, so to say, right? And solution is a complete assignment, right? It satisfies all constraints, right? A partial solution would be if I had 3 variables and I have it satisfies only one rule. I have a couple of rules and it only satisfies 1 or 2 rules, but doesn't satisfy all, let's say, all 5 rules, right? And again, we solved some things like linear programming. We were doing linear programming, those who had the linear programming in my algorithm class, I believe, right? Something like that happens there as well, right? But this is more general, right? So in this particular case, this is, again, map coloring problems, which can be solved in many different ways, right? That's a book example. And they give Australia, right? Maybe they're Australians, I don't know, right? And there's, of course, Australian capital theory. And, of course, the task is, how do we color them in as little colors as possible? Here you see 1, 2, 3, 4, 5, 6, 7 different colors. I think they're all different, right? That's one way of solving a problem. If you have no constraints, right? You put all the colors, you match all colors, right? So if you want to model this type of problem as a constraint problem, right? Well, constraint would be no adjacent states have same color, right? So variables would be the states, right? What do they have in Australia? Who has been to Australia? Anyone? Oh, cool. How did you happen to go there?
With my parents.
Okay. So, did you get bitten by any scorpions or any snakes?
I got stung by a jellyfish.
Oh,
jellyfish.
Jellyfish.
Yeah.
Okay. So, would you recommend going back?
It's not as bad as everybody claims because I only saw 2 spiders.
Okay.
Maybe this big, but it's not as bad.
Yeah, not as bad. Okay. All right. We'll keep that in mind. All right. But so yeah, I mean, I've seen some of the beach look amazing, of course. And I have some friends who actually work somewhere there, but of course it's also quite expensive in the big cities. So, but our task is they have this nice English, of course, owned by English, right? All these nice divisions, mapping, right? They just drew a straight line. In those days, 19th century probably, right? Or 18th, no, probably 19th century, right? So all these territories, right? But, so how many colors do we need? 1, 2, 3 for sure. I think 3 colors should be enough, I think, right? 3, and let's see, 1, again, yeah, I think 3 colors should be enough, I think, but I don't know, right? I think, but of course, as we know, in general case, it's 4 colors, right? We need 4 colors for planar map, for a map, because we don't count mat touching like it doesn't count. You need some edge between them. Okay, right? State territory, right? So constraints, that's primary constraint, right? So we could do we call them constraint graph, right? And then we solve it basically, right? And again, in general case, it's 4 colors which I mentioned. So one way of doing it, right? We draw, maybe make this a little bit bigger. Again, yeah, let's make this a little bit bigger. Right, so Western Australia, Northern Territories. So basically, whichever have similar edges. So again, in solving problems, of course, transferring something to a graph problem is usually one of the steps you can try. Right? Maybe you can model this some sort of graph problem. For example, Tasmania here, of course, is a separate graph with one node. Right? And again, you guys all know these are nodes, these are edges, right? It's a graph problem, basically, right? So, let's see, this guy here has collections between Southern Australia, it's connected to everybody, right? So it's 1, 2, 3. Yeah, I think it nicely transfers into 3-color solution, right? Constraint graph, basically, right? So, right. So that's one example of a problem you can solve, right? Basically, right? So, right. So, right. So basically, how we solve them basically, how we approach the solutions, right? We check, okay, does this satisfy all the constraints? It's very easy to check whether a problem satisfies constraints. I mean, usually it's enumerable, right? For a big problem, the finding solution is harder, right? Verifying solution is usually easier, right? Verifying the constraints, something comes to you with a solution, that is easy, relatively easy, right? Finding solution, right, might be hard. Again, another problem, right, is so-called job shop scheduling problem, right? You have a set of jobs, which basically have a sequence of tasks, right, on a bunch of machines, factory machines, I don't know, CNC manufacturing, right, and you want to complete all the jobs without violating any constraints. So this is sort of classical optimization problem, right? So variables, right, represent a task. Domain of each variable is the possible start times, right? And complexity, of course, comes when you have to consider all these constraints, right? So which comes first, right? You also, maybe there's some things you cannot do, like if you're making a car, right? You probably cannot weld the doors off before putting, I don't know, the seats in. I don't know, right? But something like that. There's some things you cannot do, right? You cannot put all wheels before you have actually the wheelbase, right? And not have an engine, right? So obvious things, right? So that's some. So objective is, of course, is to minimize the completion time, right? So we can find a solution as usual, right? On something that satisfies these constraints, and then you want to see is that the best solution, right? So there's different types of constraints. You have precedents, meaning which come first, and also things which cannot be done, right? Meaning maybe machines can do, there's a machine which does a specific thing, maybe there's a general machine, right? And you want to see, okay, you cannot do two jobs at once unless the machine supports that, right? So could be pretty difficult, right? Here you can see an example, right? So yeah, or previously, or basic definition of CSP, right, was basically that we use the discrete or integer values, right, or negative, positive, but still, right, finite domain. Well, finite, potentially finite. I mean, you define, range, right. As soon as we start adding floats, values, what happens? Of course, the solution space becomes potentially infinite. Also, of course, we have infinite domain of numbers, right? So instead of all integers or all real numbers, so that of course makes things quite a bit more difficult, right? Also, like I said in the previous course, one of the courses, you look at the linear constraints, right? And those are the best studied problems are where you have linear constraints, right? Limitations. However, in real life, you might not have just a linear constraint. You might have some, quadratic, some non-linear constraint, which does not have these easy solutions, right? So continuous domains, variables can be any range, binary constraints, global constraints, right? So let's look at one more example, right? And let's see this example. 2 plus 2 is 4, right? Solving 2 plus 2 is 4, again, different ways of doing it. Right, it's called the cryptarithmetic puzzle. I know it is one of the homeworks. I think in algorithms, which class they give you homework? Not this particular puzzle. Who remembers? Who has had this puzzle? I know I made some of you had solved in algorithms, right? Yeah. So of course, one way of solving it without any of constraint, you just do brute force search, right? For this sort of don't have to formalize this completely, right? So let's see what the approach here is, right? So you have this in this particular approach. This is from the book, actually, right? You have this graph, right? Each letter represents a digit, right? Different digit, right? So and you have some certain rules that need to be followed. And also, let's see this here: 2 plus 2, right? O, right? Yeah, O, right? There. What are these C1, C2, C3 here, right? These represent carry digits, actually, right? Potentially, right? Those have to be carry digits. I'm not quite sure about this. Okay, let's see what they say here. So the constraint hypergraph, right? All different constraints. The square box, they all have to be different. So that's a constraint that says it's just a box, right? Green box, not black box, right? Says that it has to be different, right? On column additional constraints, right? That basically columns, you had O plus O, right? You are supposed to get R, right? It leads to R and you carry digit. Okay, yeah, that makes sense. Okay. Then you have two W's, right? Add two W's. Also, you come in, you have a carry. So WW, carry comes in, right? So W and C1, and you have U and C2 potentially, the carry digits, right? Kind of complex way of setting this up, right? Modeling the problem, and then you have second carry digit, which could be 0, right? And then you add plus two twos, right? You get, again, what do you get? Well, you get O, right? You're supposed to get O, right? And then you get, potentially you get carry 3. Well, the issue I have is this maybe is that I personally, if I was modeling this, I don't know, I would probably add some maybe arrow directed graph I would like maybe, because like here, two twos, they lead to O, right? Here O is actually the input, right? I think better. But again, it doesn't really, it might not be crucial which are inputs, which are outputs. Basically means these participate in these. We have 5 constraints. And so apparently this actually turns out it's enough, right? So F, 2 Fs, well no, 2, let's see, F is equal what? So basically here F equals carry digit, right? Yeah. So what do we know from this problem, right? Can we solve this in our head? Can we? Yeah, I'm sure we can. Right? I don't know, I mean, I maybe knew a solution a long time ago. I think we could, right? No?
We don't understand even what's happening.
No, you don't understand what's happening?
No.
Okay, but you understand the left problem on the left side, right? You remember? Well, okay. So it's fine. Okay, so let's solve it. So, I mean, it's how if I was an AI agent, like how would I solve this, right? Let's do this. I mean, this may be more fun than actually, you know, doing it, letting computer do it, right? Because you agree 2 plus 2 is 4, right? Yeah.
We understood that.
That part is easy, right? So let's see if we can draw this constraint graph, right? And that's kind of, so, there we go. 2. Well, I need to carry digits, right? So let me, oh, come on. 2, 2 equals 4. Right, plus, right? Okay, so we have our constraints. So there's one constraint, I'll do this constraint map. So one constraint is that they all have to be all diff constraint. All diff, right? And this means that this applies to, I guess, how do they do this? F, right, again, I need to use that, I need to use round ones, right? Yeah, okay, so F, right? I need some color change then here, right? So all diff F, all diff 2, right? Then we have W, right? O, and we have UR, right? 1, 2, 3, 4, let's see. 2, 4, O, no, we only have UR. Right? UR, not you. UR, right? So that's one constraint. But unfortunately, right, things are not so simple. I guess you can't really read this. So this constraint is all different, right? So it means all this represents a digit, right? Integer from 0 to 9. Well, okay, this can't be 0, right? Control Z, right? But actually also it should be probably said that this is not a 0, right? If you think about it, right? This is not mentioned in the book, I don't think so, but it technically should be a constraint, right? Not 0, so F is not 0, right? Non-zero F on 2, right? I would say add those actually, I would add a new constraint. Not 0. Not 0. Right? Okay, and there are like a couple more constraints. So we have what? OO, right? Oh, and we have these carry digits, like potentially, right? So basically, we have carry 3, C3, C2, and C1, right? So what happens? We have two O's, right? Basically, they lead to, we can make these constraint boxes. One of them was that F is basically equal to C3, right? right? In fact, I would probably just write here, right? F equals C3, right? Equal, two equal signs, right? The programmers use two equal signs, right? So that would be one concept. I could actually write this, right? Not zero, all diff. Again, not completely formal, but hopefully you're starting to get the idea. Yeah. So maybe somebody has a solution, but don't cheat. Don't put it in a solver, right? I'm sure pretty much you put into ChatGPT or Google search, it'll find it for you.
No, it's down.
Excuse me?
It's down.
Google's down or ChatGPT?
ChatGPT.
Awesome. But yeah. DeepSeek, yeah. You can run it actually on your own computer, by the way, if you have enough RAM, right? So, yeah. I mean, for example, I have Microsoft has a 5 model, which is like 14 billion parameters. You can run it on your own computer. You know, don't need anything too fancy. Even with the CPU, if you have a CPU, it takes you maybe a couple minutes to get an answer, but you can get an answer if you want to. Yeah, but if you have a GPU, you are in good shape. Okay, but right. So let's go back to our constraints. I forget how many we have, but let's see if we can figure this out without the book, right, or any cheats. Right. So if you add two O's, right, basically it will generate the C1, right? So basically an R, right? So R, right, is involved here, right? Potentially. So 2R, right? So it basically O plus O, right? O plus O equals C1R. And C1 could be 0, right? It's okay, right? Potentially, but we'll see actually we can solve this, right? And so same goes for two W's, right? But they get C1, right? Two W's plus C1, right? Why? Capet?
Yeah.
Okay. So this is C1. C2, C3, right?
Okay.
Right? So you add two O's, you get R and C1. You add WW plus C1, right? Which is U, right? And so you go. I mean, again, second grade? Yeah? It's coming back to you, right? A little bit, right? All right. So, okay. And so same thing. Again, I don't have much, my pen is I guess it's too big. So here it's O1 WW. I'll just say W times 2, right, plus C1, right, is equals what? C2 and O? I think so, right? Yeah, no, U. I mean U. Where's U? There, right? Yep. Okay, it's equals U, right? So those are all involved. Okay, I think we have another constraint. So now we have two T2s. Yeah, this is going to be one more constraint, right? It's going to go here. So basically, 2 times T times 2 plus C2. No, plus C2 equals what? Well, actually, that's the same one here, right? It's equals to FO. Well, I mean C3 on O. There, right there, all right. Okay, but this is of course all messy. Okay.
Why aren't we
Okay, to me?
C2 anywhere?
Oh, this to me?
Why aren't we referencing C2 anywhere?
Oh, this should be here. I'm referencing here. I just forgot to draw a line. And also it comes out through here, of course, right? Yeah, so they're all like this, right, of course. So again, you could say, I'll draw arrows, of course. I would like to draw arrows, of course. Arrows, right? Arrows, right? Okay, so yeah, this is a way of formulating, okay, these are all, but now how could we solve this? Right? So of course, we have constraints, right? If we are humans, right? You could just start putting some values, not the brute force, right? Again, we could just start generating, for those who remember the assignments like these, we could just generate, all the possible combinations and then check, is this a solution? Is this a solution? Is not a solution, right? But here we have lots of solutions. First of all, we can cut off a lot of search space, not 0. F is not 0, 2 is not 0, that's good, right? Immediately cut off those solutions, right? That's already, I don't know how many millions of potential solutions, right? So we have only 6 different digits. So we have a lot of, seeming a lot of space. So first of all, we know 2 and 2, So 2 is how much? What's this? From this we can generate, if we are humans, a new constraint, right? That what t is what? I would say over 5 or more, right? It cannot be 4, right? You all agree? It cannot be 5. It cannot be 4 because 4 plus 4 is 8, and we do not have carries. When you're adding two numbers, you're not going to get more carries than 1, right? So carries actually, right? So another constraint is, right? If you think about it, of course, is 1 or 0, right? That's it. There's only two possibilities, right? For these particular carries, right? You cannot get 2 anyway. No, there's no way to get 2. You agree?
Yes.
Okay, so far we're good. So t is at least equal to 5. So that's how we could make some more constraints actually, right? And let's see, can we actually get a solution, a human solution? So O and O. Okay, so the question is, can we, well, first of all, the good news is this repeats, right? It comes back into play. Now
Can we
let's,
assume that f is 1?
well, yes, I think so, right?
Yeah.
I think that's a good assumption, right? It cannot be 0, it would be silly, right? So it cannot be 2. There's no way to do, yeah. So f is 1, so this means there's no other ones here, right? So this is 1. So let me delete this f, and I will, can I do this? Oh yeah, I can do this with my finger, right? Okay. So this is one big fat 1. Good, you see? Oops. Come on. All right. There we have our first solution. I mean, first real, right? You all agree, right?
Yes.
Okay. So how about the thing is, these are, right? The only sort of hint is this O and this O, right? So now it's a general problem within these constraints, right? Because when you transfer the specific problem into this general problem, so well, you can just, now you have search space lower, you could try O and O basically, right? What's going to happen, right? So if you put 2 5s, I don't know. What happens if you put 2 5s? You get 0, right? And is that enough? So if you do 5s, this has to be 5, right? Can this be 5? It could. Okay. First of all, we know this is going to generate a carry, right? So the question is now about these carries. So this carry is 1, right? So this is so at least 4, 5. If this is 5, 5, it would be 10, potential 11. Right. So now this I think is this would be actually trying to solve it would be. I don't know. Let's do 5, 5. That's 0. Let's see. Let's try. Okay.
Let's try with 3.
3. Which one? This?
O is 3.
Oh, it's 3. Okay, let's try it.
O has to be a fair number because t plus t.
Well, no, but you have carry. You have carry.
Yes.
We have potential carry. So that's right now. It's that's what I'm saying. It doesn't have a complete. So this is what 6, right? And this is 0, right? Okay. Now, can we somehow? Maybe there's multiple solutions. It's possible. It seems to me, it seems like there's not enough constraints, right? So
W is 5.
let's say 5, right? And this is 0, right? And this will be 0 then. 5, 5. This will be a problem, right? I'll tell you why. Right? This is what? 0. This is 1.
And then these are 6.
6.
Oh no, but then
6 doesn't work. Okay, 6 doesn't work. 7 works. No. 8. 8 works. 8. 8 works, right? 8 works. 8, 7, right? No, it doesn't. Scheiße. I'm sorry, pardon my German or French, right? But this, you see? So we've reached an impasse. So this is the mean. So this is 3. This actually drives solution. So it seems like it should be. It seems like we almost have solution, but so this part here, where we get 6. So 6, and then you need to use this. So if this was 4, no, if this is 5. Let So let's start it over. We could just write, somebody could write the program now, of course, by now, right?
Kill it, so backtracking photo.
Yeah, you had one, right? Yeah, so, but
But why couldn't it be 6?
why couldn't it be 6? What do you mean?
I mean T.
T, 6? Because R is 6.
Ah,
Yeah. So there is, it's not so simple, right? It seems, like, so this O kind of throws a monkey, a wrench into our plans, basically, right?
I was thinking maybe that the O's cannot be 3.
Okay, they can't, obviously they can't here, right? So, because this doesn't change anything, right? We need, because it has to be 3, but then there has to be 6, and this is 6 here, so it doesn't, there's an impasse, right? So we can't, so this is not a solution. This is not a solution, right? Right, so this is obviously, okay, so now these carries, right, you can leave. Right, so if this is 1, 1, 2,
6, 6, and T is 5,
okay, let's try this. Can we do this 1, 1? Okay, but this is 1. No. Yeah, we already failed. F is 1. So 1 doesn't work. So 2 would give us 4, and then we need 7 here without carry. Can we try that? 4 is 8, right? No, 2 and 2 is 4, and this is 2, and that has to be 6. Would that work? Let's try this. Or is it not as simple? So 2, 2, 4, right? This is 2, right? We know it's 2, so this is 6, 6 without carry. 6, this is 0, right? This is 1 and this is 0 then, because we have big, okay. So now what can we put here? I don't think we can put, we cannot get carry. It doesn't work, because we have 1, 2, 4 taken, so 3 plus 3 is 6, that's fail. Right? Because we only have 6 here, so it doesn't work. So let's get, my finger is gonna, fall off or something, I don't know. All right, so I guess I can do this, right? So come up. Oh, it does work somewhat. Okay. So 2, we tried 1 doesn't work, 2 doesn't work, 3 doesn't work. I think so. This is an easy way of doing it, right? You only have checked a couple times, right? 4. So 4 plus 4 is 4 plus 4, right? And then we can finish the lecture. 4 plus 4 is 8, right? And this is 4, right? Okay, that means this needs to be 7, right? 7, 7, 0. Okay. And now we have a problem. We need something which doesn't have a carry. 3, 3, 6. I think that's a solution, is it? Seems like a solution to me. Yeah. Right? 3, 3. We solved it. All right. So 700, 300, 734, 734 equals 1468. Certainly looks good to me. All right, super. We solved it. We don't need any. Who needs thinking AI? It's down anyways, right? So, okay, right. So, but let's go to this. So, let's go to how potential solutions would be. I'll save it. Yeah, save the solution. And if you find that maybe there's an alternative solution, right? Maybe there's an alternative solution to this. 2 by 2. Come on, why can't I save it?
why did you decide that F was 1?
Because numbers start with, when you add 2 numbers, right? You cannot get the highest carry is 1, right?
Ah, okay.
Yeah, you cannot add 2.
Yeah,
Right?
the biggest is like 9.
9 is 18, right? That's all you can get, right? If you had 3 numbers, there's puzzles like this is 3 or 4 numbers, right? With, those are harder because you could potentially have multiple, carry. So I don't know. I wonder. I mean, the thing is, these puzzles were made in 19th, 20th century, right? Before people who made these, I mean, they did this in their heads, basically. Solving is fun, but setting it up is much harder, actually. Coming up with the puzzle, right? So it'll be interesting to see. So 2 plus 2, 2 plus 2, 4, right? All right. But you got the idea how we can model this constraint graph, basically. All right, let's see, keep going. Right. So, basically, we did this actually, right? We did this in our puzzle, right? Constraint propagation, basically, right? We added extra constraints, right? We propagate some extra constraints such as C could be only 1 or 0, F cannot be 0, and F actually is 1, actually, right? And then our search space, the whole core idea of all of this approach is that if you have a really large space, by adding these extra constraints, we can really cut off the problem before we do any type of what you call, domain specific, right? We transform this problem, from a specific math problem here, sort of, like into more like a less, into this puzzle, into this general graph problem, basically. So our consistency, right? So involves changing pairs of variables, ensuring every value is consistent, right? So, right, so we want to, right? So basically, you check whether there's a consistent path, right? There are different ways of solving this, right? And of course, there are also these so-called global constraints, right? So basically, you have something complex relationship, right? You want to, you need to add this, right? Show, okay, maybe 5 variables have this constraint. Like in this our case, we had a constraint at all diff, which is for everyone. But we had a constraint not 0, which applied to f and 2, right? F and 2 could not be 0, right? So bounds consistent, right? Okay, and we get to our favorite puzzle, Sudoku, right? Actually, right. And I remember, I think you made a solver for this as well. It's a classical constraint propagation problem, right? Right, Sudoku solver, right? And same approach, right? What kind of constraints are? Who plays Sudoku? A couple of you have done it on it, right? Sometimes on an airplane, yeah, it's a good way to spend a few hours if you have some, right? So, do we know a solution to this one? Can we solve it, right? Again, the brute force, again, so remember what was the problem with the brute force solutions here? Well, in general, if you're searching the space, right, we could just throw random numbers, right? Here, right? And then check, but if we are going to solve this, right, we want to check it in a, for allowing for these constraints. So what kind of constraints? There are 3, right? 3 big constraints, right? This has to be all different, and all different, right? 3 type of constraints, basically, right? For each box, right? So there's actually technically 27 constraints, technically, I guess, right? 9, 9, 9, right? I think that's how you're calling it, right? And of course, the fun is for our brains, right? Is how to check these constraints, right? To find a solution. Okay, let me see. I guess since let's see, maybe we'll go back, let's go through the theory, and then we'll try to solve this Sudoku. Maybe, all right, we have time, and I guess we'll not take no break, right?
Yeah.
You guys want to go home early, right? So, okay, so plan is we will go through all the theory for this chapter, then we'll solve Sudoku, and also I want to make maybe, there's a solution, I don't want to look at the solution, no, that's not fair. No, not going to solve solution. We'll check it after. Okay, so here, yeah, that's exactly like I said. There's 81 variables, all the squares, 27 constraints. We'll solve it ourselves, right? We'll check, that's a cheat code, but we'll check it ourselves, right? So backtracking search, right? So how we do it? We start checking, right? And if we have a problem with one of the constraints, what do? We go back to where we did not have a problem and look through the next one, right? So, who remembers what was the problem? This approach, how you could make an evil Sudoku puzzle, right? What is the idea? Like, there is a difference when you start. Where do you start searching? Do you start at the beginning, or do you start at the end or middle, right? Where do you start checking, right? It's sort of like you have these constraints, right? But depending where you start, right, you might have a longer exploration path. You start maybe at the beginning, right? Depends how the puzzle is constructed, right? Maybe random approach might be better. Where do you start checking, basically, right? Because you know how evil your nemesis of the constructor was. So variable and value ordering, right? So again, this is important. Basically, check if there's fewer options, right? there's this idea, general idea, you choose where you have least options, right? You will hopefully quickly identify the conflicts, right? You check, remember like when we solved or 2 plus 2, right? We tried where there's least conflict, there's only a few options, 0, 1, right? You don't have too many options, and then you hopefully, you don't have to proceed too quick, you don't have to go too deep to find the problem, or maybe you find a solution, right? But again, another heuristic. What's a heuristic? Heuristic, right? That's a rule. It's basically like an approach, like a hint what to do, right? Idea is that maybe if you have to select variable, right? Maybe select one which is involved in most potential constraints, right? So why is this idea? Because it's important to check these type of variables, because they are likely to cause the most conflicts, right? You check, okay, like so finding O, right? This O is involved in the most action, right? This O, right? So checking that one in our approach, that's what we did. We had our easy ones, right? And then we actually tried finding O, right, first, because that was the one which kind of led to other things, right? So least constraining value, right? Right. There are different strategies, right? So again, maybe you try to interleave, meaning you switch things up, right? There's another approach, basically. You try to switch, maybe search, right? Meaning explore the solutions, right? Maybe you check some extra constraints, maybe some extra what you call add some extra rules, extra heuristics, perhaps. Okay, so right, so intelligent backtracking, right? Backtracking again is the idea of going back to previously looked at solution, but maybe with less variables, like with less constraints, basically, right? When you tried, maybe you tried in our solution, right? When we tried 3 here, right? It didn't work. We backtracked to the position where we did not choose O values. We only have F value, right? We backtrack to solution space where O is there, right? So now back jumping. Sometimes there is a way of jumping more, right? There are different approaches, right? Maybe you can jump immediately back to the problem child, basically, right? Constraint learning, right? Sometimes the algorithm can learn, actually, right? Smart algorithm, right? So basically, you add extra constraints when you're exploring these fails, right? Because you're going to have fails, right? Also, an interesting idea is no good, right? This guy is no good, right? So, key concept, basically, you add some variables, right? So, this is going to be a bad pass, right? So, combinations, basically, that are basically going to be bad, right? So, another approach we can do. And of course, again, this will lead to, we'll see some examples of 8 queens problem, of course, right? Where else we use this local search, right? Minimum conflicts, of course, heuristic again, right? Look for least conflicts, of course, right? Real-time solution could this been actually for how do you schedule? People are fighting for, Hubble Space Telescope, right? You need to, you want to look at some specific galaxy or whatever, right? But of course, everybody wants to get some time, right? It's only one Hubble Space Telescope, right? So of course, scientists need to schedule, right? So there's lots of constraints. I'm sure there's different countries involved, right? Politics and so on. You could theoretically schedule this as, okay, this guy gets 5 hours, this guy gets 2 hours, right? On this time of day and so on, right? Lots of potential conflicts, right? So mean conflicts heuristic, right, has been used before actually this. There's also taboo search, right? So basic idea is to avoid these local minimum states, right? You have these bad areas or taboo meaning you cannot go there at all, right? So what else do you want to set? So I think there's a the composition, the other approaches. So this is kind of short chapter. So yeah, we have time. Let's see, I have 2 things I want to do today. Still, I want to generate a problem set for your homework, for your vacuum cleaner, right? To check something. We'll see. Maybe we'll do that. But maybe let's solve the Sudoku puzzle, right? Are you up for that? All right. Let's see. So we have our 27 constraints, right? And I think this one we can solve it. I'll use the smart thing here. Let's see if we can do this, right? Or maybe this one here, right? Yeah. Oh yeah. Okay. No. Oh no. Okay. So we have 27 constraints. So what's the first number? Let's think.
One.
One. Where?
First row, third column.
This one or here? Well,
But yes.
but we have two problems. We have a where?
Like the first row.
Yes.
Column.
Here?
No, like the first square.
Like first
Yeah.
possible one.
This or his? No, come on.
The upper one.
This one,
Yes.
right? But the thing is, okay, the question to me is, okay, this it's a well approach. We have two choices, basically, one or one, right? So, this is okay. We would do this if we had no, like, guaranteed, completely constrained choice,
There
right?
is a safer option for
Yes, that's what I'm looking
At
for.
the very bottom.
That's what I'm saying. Let's do a safer option. Where?
At the very bottom.
This one?
Yes.
Yes, I think so too, right? Look at this. One,
Mm-hmm.
one, right? Not allowed. So these three are off. So this is actually guaranteed. There's no other way. Nothing else you can put there, right? One has to go there, right? You all agree? Agree. Okay. Right. So let's look at number two. Unless I see another. Okay. So one here, one, no, one, no. Okay. Too many ones. So two. Let's look at number two. This is what I do if I was on a bus ride, and this is the approach I would do. What about two?
We can use 4 for the same square.
Four?
Yes.
Yeah, four has to go here, right?
Mm-hmm.
Indeed. Very good. What are we left with here?
6.
On six.
6 and 3.
Six has to go here, right?
Mm-hmm.
Yep. There we go. Right. And what's left? 3?
Yes.
Okay, this was easy, right? That looks pretty good. But, so, and now we have one here, right?
Mm-hmm.
This leads to yours. One has to go here, right? There we go. Right. Excuse me? So now, okay, how about ones? We have
Left corner.
this one.
Yes.
What would be here?
No. The one should be
Here?
at the third row. At the very bottom.
Here?
Top corner or bottom corner?
Top corner.
Top corner.
Top left or right?
Bottom box.
This one here.
Yes, and top corner of that box.
Here?
Yes.
What should be here? One?
1.
Yes.
Yes, because one can only go here, one can go here, one can go here. So you're right. Very good. All right. So we are actually making really good progress. So basically here we have two ones here. We don't really know where.
Mm-hmm.
We don't have two ones here. So this is like either off. We don't want that, right? Okay. So what do we want to do now next? Well, now twos. We don't know anything to do once. We proceed again. Guarantee twos, which is here. Do we have two? We have to open, two here. Two. Let's see. Seems like
The
this.
second square, middle row, below 9.
This here.
No. Sorry.
Two is here. Take it.
Yeah.
So now two seems like really kind of too open right now. I guess so. Here we can have two here as well. Okay, so let's leave it for now. Let's do threes. Threes here, three here. So we only you need three. Yeah. Okay. How about here? Oh yeah, the one again. Too many open. I found three. Well, yeah, because we don't have space for three here. No three here.
I think we can do a 9 in like the last box on the bottom.
The here? No.
Some no, but the
Here.
nine, yes.
Yeah, because 9, you're completely right. Yeah? All right. So 9, 9, 9. Here we have 2 9 possibilities. No. Here I get 2 possibilities of 9. Okay, that's interesting. So,
The third mouse, like the rightmost corner.
this
Yes, the no, upper corner. Yes, 9.
let's think about it. Yes, 9. Yeah, you're right.
We can go with the first column. We can put 3 at the last cell.
Yeah, because you're right. Because that's the only place you can go, right? We need a 3 here, and now of course, what's missing here? 2, right? Very good. So this means the 2, well again, still open 2 spaces, right? Okay. All right. Very good progress. So what do we have left here? 7 on 8, I believe. So 8 has to go here, right?
Yes.
And then 7 is here. Fantastic. So what do we have left?
4.
4 on,
5.
okay. No, we can't, nothing there yet. Okay. So who can suggest me something else?
In the 8th square, above 9, there is 7, I guess.
This one?
No, 8, like the complete square.
This one?
It's 9th square, so.
This one is 9, this one?
Yes, above 9, there is 7.
7, let's think about this. 7 not
Because,
here, up here?
It likes 5 and 3, so, and neither 5 nor 3 can go there.
Yeah, you're right. But the thing is here, how about 7 here?
Neither 5 nor 3 can go in this square, and this.
Ah, we need 5 and, you are very smart, this is very smart. You need 5, 3 and 7.
Yes.
So 5 and 3 cannot go here, so only thing left is 7. Very good. So that means now 5 and 3, and we don't have any yet constraints there. Very good. Can we do anything about this square? This looks like there should be some constraints here. 5, 3, 7, 9? No. Wait, let's see. 2? How about 2 now? Yeah, it's too open yet. So, here maybe we can do something here. So we have 2. No. Will we solve this? I think we'll solve it. But because the point is, of course, we are doing these, so far we're doing great, because this is relatively not the hardest puzzle. We have this single step, like there's only one move, but notice from the beginning, sometimes the moves we have multiple choice. And the idea is always go for the most constrained ones, right? Because that's sort of like, you don't have any other choice, right? Or you have least choice, right? So this will lead to conflicts or potential solution. So far, we are doing everything exactly. We haven't made any choice. It's all been straight sailing, right? So, let's see, what else we do here? Okay. 5, 5, 5. Okay, we didn't, okay, let's do so sixes. 6 here, so no. Come on, 6, no. 7s. Okay, we need 2 7s here. Okay, yeah, I got 7. 7, 7. So 7 has to go here, right? Yes. Okay. Now, what about other 7s? So you have 2 7s here, right? 7 here, right? Okay. And how about 7s here? Yep.
Then the 7. Yes.
Yeah? Okay. Yeah, I think we have solved the 7 problem. Alright, so 8 problem. 8 problem here. So what do we have left? 2 and 4?
2 and 4, yes.
Yeah, 2 and 4, we don't really have information there. Okay. 2, 2, 2, 2 and 4. I'm sure there might be something smart, like you figure out this extra concept. 5 and 3, we don't have anything extra. So how about 9s? 9, 9. Do we have 2 9s? No, nothing helps. So 9 here. Oh yeah, we have it.
Oh,
Come here.
no, sorry.
No? 9 here, right? Yeah or no? You don't agree? 9, 9, so that has to go here.
Oh, yes.
Yeah. Okay, so what's in the middle? So you need a 5, right? You need a 5 and you can only go here, right?
Yes.
And this means the 5 has to go here, right? Because why? Why does it have to go here?
Why?
Because it's go here.
Because
Yep, that's 12.
Okay.
no,
Yeah, no, we don't know yet.
no.
Did-
Because like the rows.
You see? I mean, I don't have 5 here because I have all field.
Yeah, but no. Five, like,
This here?
yeah, it has to go there either.
Why can't it go here?
Because
Oh, 5 has to go here, right? Because 5 has to go here. I don't know yet, but somewhere here. You're right, completely. And then it means 3 has to go here because 3 is not here. So that's good. So 2. But I still left is the 2 on question of 2 and that's 6. 2 and 6, right? Okay. All right. So what do we have left here? So we have what? 4 and 5. Yeah. Okay, that's not good. So we did 9s.
No, okay, yeah.
So we did 9s. You have 2 laptops?
Sadly.
Oh. One for work and one for play, right? Yeah. All right. Yeah. Yeah. You don't know how many laptops I have.
Weird flex.
It's it's a weird flex. It's more than 10 basically, right? Yeah. Yeah. So.
One for each class.
Yeah, well, I should really do that. No, I get, but it's basically mostly just over years you accumulate them and you don't throw them away. You fix them. The worst thing is try to fix a laptop. You can fix a 10-year-old laptop, but it's not really. It's kind of mostly for fun, not cost efficient. So, anyways, all right. So let's finish this. I think we can finish this so that I can get your homework set done. Now. What do we have this here? So what do we have? So let's start. So one thing we can do is, of course, one approach is you cycle over, right? You do 9s, you do 1s now again. 1, 1. Here 1, 1, 2 possibilities. And we don't need the other one. Oh, here, yeah. So 2s. What is the issue with these 2s? We have 2 here. We need 2 here, we don't know yet where. Looks like there's some problems. 2s go here, right? This means that,
Oh, we have on it.
no, you see, 2 going here, right? You could, of course, if you play this on like an application or you make your own app, they usually have the option to suggest a couple of choices. You can do this sort of like, suggest, okay, I can put 2 and 4, right? Sort of like, so you have to keep track of this, right? It's okay, you can put 2 has to go here, right? You don't know where, right? And because 2 has to go here. Well, actually only 2 places, right? So, still open search space. So 3s are, I think, done. 1, 2, 3. No, not done. No, we still have room for 3s here. 3 or, oh, here's 3. Yeah.
Yes, yeah.
3 has to go here, and this means that 3 has to go here, right? Yeah, okay. Good improvement. So how about 4s? 4s are trickier. We have a 4.
That's 5.
Which one? 5?
Yeah.
Yeah, it probably has to be because 5 cannot go here. 5 cannot. Yeah, good choice. Good point. So this means that 4 has to go here, right? So now this means that 4 has to go here, right?
Yes.
And this means that this 2. Finally, we get our 2s.
And
Now I
then
see.
then the upper square, there should be 2.
Which one?
The right one.
This one is 2, you're right, and this is what? Which one is this? I can't, I am like getting tired. 8, right? Yeah. Okay, I think now I think it's almost off. So 8 here, right? 8, right?
Yes.
Yeah. And where's 2? Not here, so 2 is here, right? 4. Yeah, 4, yes, and 6. I think they're all solved it now, so somebody can come up. Who wants to finish this? Who will? No? You can do it. Come on, who can do it? Let's do it. Let's do it. Yeah. All right. should be doable.
No pressure.
I only have a timer, 5-minute timer, but
Someone wants help?
Like there is a row with 8, like the fourth.
Oh, this is
Column,
8.
fourth
8 here
column.
goes. Yeah, 8 goes here, right? Yeah, 8.
Fourth column, it's almost complete.
Yeah.
So this should be
No,
something.
column from
Yeah, well, we're doing it correctly. So that's something what number? 4, yeah, 4. And this means the 4 should go here, yeah. Now we have a 2 and 5.
No, shit, it cannot be 4.
Why not? Oh, you're right. Sorry. So use this. That's undo. Come on, do this. Oh, reverse. I think. Yeah. Oh. So that's 4 for sure. So we have what? We have 3 numbers left there. 5. 5 has 2 spots. 2.
Start now, moment.
Yeah. Yeah, we don't see this. Seems like okay. No. So what can we put here? 4 here. Yeah. Yeah. 4 here.
And
And
then 1.
1. All right. And then 1 here. Yeah.
The right one, the top will be 5.
Yeah.
Yeah.
Because why? Because there's two space spots. Not yet. 5 is. We don't know yet. We don't know.
5 is here.
Oh, you're right. Yep. There's no choice. It means that we should be able to solve this.
Middle column, the last square should be 6.
6? Yeah, you're right. The 6 is there. You're right. 6. Go 6. 6, yes. No, you can't. There's no 6.
I mean the column in
Like, where?
middle column,
Yeah.
the last square 6.
Yes.
Yes.
Yeah, because 6 is up there. Yeah, you're right. Because now suppose we got just your missing number. So this is
Here.
right. That looks good. And 2 is so 2. No, not yet.
We can put 4.
In which place?
Left.
Here. Yeah.
Left.
4 here. Yeah, 4. And this means 5 here, right?
Yep.
That's good.
So the left one, top middle is 5.
This. Yeah, you're right. Yeah.
So, 2 can only go here.
Yes.
Yeah.
3, 4, 5, 6, 9.
Very good. And now we should be finished.
Here is 9, here is 2.
Yep. Let's double check with the solution. We have a cheat here, so I will say. It's only good. How do I save this thing?
Just scroll down on the computer. I think it will stay. It will overlap.
Oh yeah, we can overlap it, right? You mean like this? Yeah, we can overlap this. Right.
It's small.
I can make it small. I can make it a little bit bigger, maybe. No, can I do it? No.
Wait.
Okay, maybe let's move this. I'll move this. Wait.
No, just a little bit.
Yeah, I think roughly. Yeah. We can see.
Yeah, it is okay. It is
Yes, very good. Very good job.
Yes.
Yeah. So it turns out instead of Sudoku, there's in a real Sudoku you cannot have multiple solutions. That's not considered a good puzzle, right? You have only one solution, right? So the hardest puzzles I think you have only start with like 18 pieces or even less, right? Yes, question.
No, about the previous one. So we kind of operated on the assumption that problem.
Yeah.
That there is only one carry, which is like 42,
Yeah.
for the t.
Yeah.
And if we're operating with an assumption that's the only carry, that is only the only solution.
Yeah.
But if we would take that there's possible carry also
Yeah.
about
The first or second one, right?
Yeah, the second one, then I found 4 solutions.
Okay, very good. So basically what you're saying is, yeah, if there's only carry 3 is the only one, then, that's the solution. But if you allow carries here,
I've basically constructed this equation, like
mm,
equation system,
mm.
that just puts possible values with these assumptions,
Yeah.
and then I can look for which ones are already used.
Exactly. Like I said, I think this puzzle, which was given in the book as an example, it might actually, it's just not completely defined. Maybe that's, again, the query question is in open one. Okay, yeah, like 10, 15 minutes. Let's see, let me go back to your homework, right, and let me generate at least one map to give you, so you can submit an answer, right? So let's see, what size do we want? 20 by 20? Yeah, something like 20 by 20, right? So the only question is now how evil or how hard a puzzle do I want to give you? The room, right? You have to go through a room, right? And let's go again. Let's see this. So let's see our homework, right? And we have how much time, right? We have no submission because which is normal because I don't expect you to submit yet, right? So, all right. So the CSV, right? Let's do this. Let me modify this a little bit, right? So, okay, so no, I assume nobody has started on this yet, right? Or has someone started on this? No one, right?
I've started playing around with the idea of
Yeah.
solve it, but I haven't.
Okay, yeah. So I'll basically do this. So starting position will be a tuple, so 1, 1, right? So this is not a battery capacity, energy cost. Battery would be 50, right? On energy cost would be what? For moving, right? Right, 1. On 5 for vacuuming actually things, right? So this is an example, right? So maybe here, I have an idea. Maybe let's. I don't like this. I mean, this really requires you to read this part here, right? Makes things harder. Which one is which, right? How about making keywords, maybe, right? X1, something like this. Would that be easier, maybe? Like, would this be better approach? No, that's even worse.
Maybe you could leave the like comments, like CSV.
CSV with comments?
Yeah.
Okay, so this will be a CSV with comments. Okay, so this will make your reading part a little bit more difficult, right? Are you okay with that? You can do that, of course, right? Okay, all right. So let's do that. But that means I have to generate this, right? So this will be comment like this, or what kind of comment do you prefer? This or this? Cache, okay. So x1 y equal 1, right? So this is battery. So battery. Starting battery. So maybe I'll make this a new line. So 1 equals movement cost, 5 vacuum cost, vacuuming cost. So this is an example, of course. So how about I'll split the x and y. Maybe I'll do those well. So yeah, let's do that. X, starting x, starting y. So now the question is which one is y? Horizontal, right? Right? Okay, now the question again seems such simple thing, but 1, does it mean this value or this value, right? Okay.
Yeah, my assumption when I started doing something was that it's like the corner.
The corner, so 1 based indexing.
Yeah.
You okay? So we use 1 based indexing for this, right? For this. That means you might be things, maybe 0 based indexing would be better, easier.
Just put a 0 maybe,
Yeah, let's do that. Let's do zeros and let's make
so it's the corner.
yes. So again, and also 0, 0, right? this one's here, right? Upper left. Value from top. From left. Vertical value from left. Right. Zero based. Right. So again, feel free to make your parser to parse get rid of these hashtags, or do it by hand, right? So okay, I think that makes things pretty clear, right? Position. So this I'll make this 0, right? Right. Could be something else, right? So this is just an example, right? So you can of course try. So this will be one example, right? You can try it on this one, of course, right? Input CSV, but let me make it. Let's generate some code to make something bigger, right? Make things interesting. So again, remember, this is a big wall here, right? You can't do anything here. It's so dirty here, you can't do anything with this area, right? So it's like the vacuum will just basically get stuck, right? And so we'll assume it's so much dirt it can't even move into the square, right? Right. So, right, or it could be actually a real wall, right? Or so, right. So, yeah. All right. Okay. So actually, this is actually kind of a really good start, all right? And let me see if we can actually generate some file. Yeah. Right. So yeah. Which ones? Excuse me?
Sudoku numbers on the screen.
Oh.
You can reverse Sudoku.
Yes.
You have the answer and you have to find the exercise.
Yes. All right. Let me get. Oh. Don't save it. Sorry, guys. Don't save it. All right. Can I do this? Yeah, I can do that. Yeah. All right. Vacuuming cost. Actually, I can't spell things today. I think this is already, you can use this to check, because it's actually, I will maybe adjust it slightly, this example by hand a little bit, and then we can finish. Actually, I will write a bigger puzzle. Where's my CSV? You guys have to finish. So I'll put something like maybe, 50 here, maybe, right? And maybe 9,000 here, right? Yeah, so 9,000 is okay. That's like the best thing you can do. Like the most dirt you can actually vacuum, right? Yeah. Well, the thing is okay, but energy it is 5, right? That's okay. So that's another thing is to vacuum everything. Let's assume it's not for one unit, right? We can say okay, let's not make things too complex, right? Assuming it starts vacuuming, it's just like it costs 5 energy to vacuum whatever is in that square, right? Unless you want to have it per dirt, right?
But does it make sense to have different dirts if they're
Because we are trying to collect dirt. We're trying to, maybe it has some gold inside, I don't know. Right, because we have 2 goals, right? Remember the 2 goals. There are 2 goals. Remember, you want to vacuum, so you want where are the task requirements? Okay. So output, total dirt cleaned, total number of squares cleared, pass, and how much battery is left. Maybe you have some battery left actually, right? So you have let me see what you have here. Right, so wow or not reachable, right? So move, right? E units, B units, okay. So primary goal, as much there as possible, right? Secondary goal is visit as many squares as possible, right? That's secondary, it's not the most important. So our main idea is to clear as much, you have 1 square with 9,000 units of dirt, that's what you want to get to, right? Actually, if you think about it. So this is actually might get things more challenging, right? The good news for you guys is that I'm not gonna grade if you have don't have optimal answer, right? But your code works and everything, right? It's gonna get really good grades as well, right? So I'm not gonna, don't have the best answer, right? The best answer will get 10, of course, right? The best algorithm will get 10, right? But if you have an algorithm which works pretty well but doesn't get the highest, like the most dirt, right? There'll be a friendly competition between you guys, right? So it'll get 9 for sure as well, right? If it's all nicely commented and everything is nicely written, right? So it doesn't have to be really super smart algorithm, right? It should work, right? So I remember early Roombas were pretty stupid, right? And it still works. You see who has had the early Roombas, how they go to the, yeah.
Really dumb.
Yeah, it's pretty dumb, right? But it actually, they figured out this algorithm which actually kind of, it's sort of like almost, well, it has sensors, it doesn't have too many sensors. It's kind of like, figures out that eventually it will clean the room, eventually, right? By bumping into things and going through, right? It figures out that some places in the room will be cleaned many times, right, basically, right? I think it has dirt sensor, I think. I'm pretty sure it has dirt sensor. Some sort of sensor which says, okay, there's some dirt. Clean it now, right? Or maybe it's even more dumb. Maybe it just keeps cleaning until
I think the one I have now is just like, it cleans wherever it goes, like.
yeah,
and
and then it starts running out. Only thing is now how to return to the home, right?
basically,
Yeah. I have a 600, like I also have a pretty old one, like at home, which I have not run in a long time. Well, partially because of the dirt problem, because if you have like kids' toys or cat, things, the early models don't work very well with those, right?
So that's why you want us to write.
Of course, right, yes, of course. All right, guys, so that's actually it, I think, for today, unless you have any questions. Right. I'll see you on Monday.